All right, so let's get going. So this is not really part 2. You are still in part 1, which ends up being a 3-part part 1 because we had one part here, one part there, and now one part here. Unfortunately, I think it's just too windy today. So yeah, it's too bad we can't finish the algebraic Bethe-Ansatz part on the outside blackboard. So we'll do it, the more conventional way here. What I really like about being in an event jointly with Thierry is that we don't communicate beforehand, we don't agree on contents, we don't agree on synchronization of stuff, but still, we're talking about the same things in a complementary manner, so hopefully you'll also see the great deep correspondence between what Thierry has just taught you now, well, this morning, and what I'm going to talk about this morning, and then what Thierry is going to tell you the day after tomorrow, second session, and then what I'll say later and things. So it's really, it's one of the great things about working in this field, actually. You got people like Thierry, showing you the way for all these things. So I hope you also enjoy having such characters in the field. It's really what makes it, at least as far as I'm concerned. Today I'm not going to go on the blackboard because, again, we've got equations to work through here. As the first time, I will flash you the storyline highlighting the most important equations and leave it to you to maybe fill in the blanks and make sure you understand the details. Okay, so for the first half hour today, we're going to complete the listing of important equations within the algebraic Bethe-Ansatz that I'll then put to use in the second bit, so the last hour of this thing. To show you more details about what Thierry already mentioned, namely the use of integrability for computing correlation functions, things in equilibrium, how you also can provide input to Luttinger theory in the form of computation of parameters and all these things. Okay, so we'll go through that. I'll try to give you a lot of details about this. Okay, so where were we yesterday? Well, we were on this web page without knowing. The place where you're actually considering the algebraic Bethe-Ansatz, and you're really doing general considerations, how to construct integrable models. What did we do? We set about developing a completely formal, in-the-air, castle-in-the-sky technology to spit out for us sets of commuting quantum operators, okay? And these sets of commuting quantum operators are then interpreted as the conserved charges of a would-be integrable model. We saw the identity giving us the generating function, so once again a Hilbert space, operator-valued transfer matrix as a generating function for these conserved charges. Trace identities give us a way to reconstruct each of these charges individually from derivatives of this transfer matrix. And that's it. Now, the core starting equation was the notion of commuting transfer matrices. Okay, and I don't know if this is big enough. Do you want me to make the equations bigger, or you're young, you've got good eyes, yeah? Very good, very good. Okay, so that's the crux of the starting point, commuting transfer matrices. That's the heart of all that is to come. And what did we do? We played some tricks in order to find constructions that gave us commuting transfer matrices. Putting our mathematical hat on, we said, there's an operation that's kind of handy when you think of changing order of things, and that is the trace. But trace over what? We need to trace over something. So we say, okay, let's just introduce a space over which we will trace. And we call this space an auxiliary space. So no physical content here whatsoever. It's just a mathematical thing we plug onto the thing. We imagine it, we plug it. That's the luxury of being a mathematician here. So we interpreted the transfer matrix as the trace over this unspecified auxiliary space of another operator, big T, which we call the monodromy matrix. And this monodromy matrix now lives in the tensor product of the would-be Hilbert space and the auxiliary space. And at this point, we have neither defined the Hilbert space nor an auxiliary space, completely general. We will do that later. Now, the point was that we can write the commuting transfer matrix equation as an equation in the trace over the tensor product of two auxiliary spaces of the product of T1 and T2, T1 being a matrix acting non-trivially in a first auxiliary space, T2 being another monodromy matrix, but now acting non-trivially in the second auxiliary space. Okay, once again, we're just doing formal trick, like black magic here. Like, wow, sorry to use the word magic. By the way, we had a question for you, Thierry. There's a card on the ceiling. Is that yours? No? Okay. So, you will understand why the suspicions fell on you. But okay, yeah, not guilty. Whether we believe you or not is another question, but yeah, anyway. Huh? No? Okay. So now the equation for the commuting transfer matrices became a simple identity between the trace of these operators now in different orders. And of course, you know that trace is invariant, trace of a product is invariant under reordering of elements within the product. But that's true for scalar valued things. And the point is that in these monodromy matrices, there are chunks that are really operators in Hilbert space. Therefore, you can't use the trick because you'd have to put the commutation relations in Hilbert space in there. But that's actually exactly what you need, because what we are doing here is eventually defining commutation relations in Hilbert space. And you'll see this appearing in a little second. So now, in order to fulfill what we're looking for, as always, is a kind of realization of these constraints. So we're looking for non-trivial monodromy matrices that obey this. And now the relationship that we have here, well, we can say, fine, let me relate this ordering of the product to this ordering of the product through a similarity transformation with a matrix R whose entries are scalar functions. They're not Hilbert space valued things, they're just scalar functions. And therefore, the reordering of elements of the trace with such a scalar function can be done. So the trace of this, trace of R, T1, T2, R minus 1, is equal to the trace of R minus 1, R, T1, T2, because R is scalar valued. Okay, and therefore I can push it through any of these things without causing anything. So if there is a similarity transformation relating this ordering of monodromy matrices to this ordering, then I've got a solution to the commuting transfer matrix requirement. Okay? So I hope that that's clear. And this is the equation that we had reached yesterday. Now, I kind of told you that this is Young-Baxter because in my mind, the whole Young-Baxter equation thing, it's really a set of equations. It's not just a single equation, but I'll just give you a few more details about this. So this is equation RTT equals TTR, okay? By the way, just so you know, in these online lecture notes, I don't use a numbering for equations. I use like a semantic labeling, which means that I can add equations without changing any numbering and things like that. But each of these equations also has this permalink. So if you like explain things, you can always use that. These links will be like perpetually unchanged, okay? So just so you know, right? And then in the notes, you just have these hyperlinks giving you these equations. That's the way it works. Okay, so now, of course, in order to have this here, I need R to be invertible, okay? So just some basic requirements of the matrix are, first of all, that it is invertible, namely its determinant has to be non-vanishing. And if that's the case, then I'm okay. I can actually do the R minus 1 is well defined. Now, also, I could write the equation in just a different order. Just a little detail here. An equivalent equation is given by this slight thing here where I invert the arguments here, but then the matrix kind of becomes the inverse of itself. And this just gives a kind of constraint on the values of the inverse of this matrix. Just what I'm trying to do here is just give constraints on the usable R matrices that I can have, okay? These usable R matrices have to fulfill some identities for consistency. And essentially what this means is that the inverse of the matrix itself is like this relationship here. You can fix it to that, okay? Because now you see our job is to find an R matrix. Yeah, we're not searching yet for the monodromy matrix anymore. We're just looking for an R matrix that we can use consistently in this construction. So that's the first constraint that we'll have on this R matrix. The only thing we know about the R matrix at this stage is that it's a matrix that acts in the tensor product of two auxiliary spaces. That's it, without knowing what the auxiliary space is. Now, there's a constraint which is really the one that's known as the Yang-Baxter relation or Yang-Baxter equation, or alternative named star triangle relation, that essentially ensures algebraic consistency of the free algebra of these monodromy matrices, namely unambiguous meaning of products of as many of those things as you want. The constraint comes from the product T1, T2, T3 being writable as the product T3, T2, T1 according to two different permutation paths. Okay, you can exchange 1, 2, then 1, 3, then 2, 3, or you could exchange it the other way around. Okay? And these things have to be equal. So changing 1 for 2, 1 for 3, then 2 for 3 has to be the same thing as changing 2 for 3, 1 for 3, and 1 for 2. This is a non-trivial relationship now that has on each side a matrix living in the tensor product of 3 auxiliary spaces. 1, 2, 3. Okay? But if I find a solution to this, if I find a non-trivial matrix that fulfills this, then I am essentially done. Okay? And you'll see a manifestation of this. So this consistency relation is Yang-Baxter. Okay? So essentially now the game is going to be to try to do something with this. And what I will set about doing here is do a succession of choices at each time we have to make a choice, where I will always take the simplest non-trivial choice that can be made. Okay? I could, of course, do it the other way around, do the most complicated choice I could do, but let's just keep things simple as much as possible. Okay, so what are we going to do now? Second step is constructing our matrices. So let's follow that link here, showing us how to do that. Well, first of all, you got to tell me what the auxiliary space is. If it's a one-dimensional space, then we're just dealing with scalars. There's no non-trivial commutation with scalars. Okay? We're not going to work with like strange things. So the simplest non-trivial choice we can make for auxiliary space is a 2x2 space, yeah, two-dimensional space. So auxiliary space is like C2. Okay? And now that means that the R matrix is 4x4, because the R matrix lives in the tensor of two auxiliary spaces. Most general matrix we write, 4x4 matrix. Okay? And these are then to be seen as just functions of these two rapidity parameters that we have in there. Completely general here. Now, because we have chosen a 2x2 auxiliary space, and we know that the monodromy matrix lives in tensor Hilbert auxiliary, it means that we can write the monodromy matrix as a 2x2 matrix in auxiliary space with matrix elements which are purely Hilbert space operators. These operators, A, B, C, D, are Hilbert space operators. Okay? And now I'm just using the usual tensor notation. You remember perhaps how to do tensor product. Essentially, you write one matrix inside another. So this is just telling you what, for example, the T1 is. T1 is the tensor product of the monodromy matrix in auxiliary 1 cross unit in 2, and the T2 is unit in 1 cross monodromy in 2. So this is how T1 and T2 look like. So I can compute T1, T2, and T2, T1. Okay? And now, I have to specify my R matrix further, because what we just have is a construction that would allow me to do R T1, T2 is equal to T2, T1, R. Okay? But the R matrix is just still unspecified. So what are we going to do? We are going to try to find the simplest non-diagonal form of an R matrix. Okay, non-diagonal, because if it's diagonal, again, everything commutes. Okay? By the way, if there are any questions, please interrupt me, because again, I'm just like showing you the story. So, what are we going to do? We've got 16 matrix elements for the R matrix. We want to have the smoothest non-diagonal one that we can have, so let's just choose one matrix that has a single off-diagonal pair, like this. Of course, I can fill it up with things, but I like zeros, simplifies things, so I just say my R matrix is this. And now, what's my constraint? I have the Yang-Baxter equation. R12, R13, R23 is equal to R23, R13, R12. So I just substitute this form into Yang-Baxter, and I look at what that gives me. This gives me constraints on the functions B and C. Yes?
We got the Yang-Baxter equation from the requirement that T1, T2, T3 is equal to all the cycles, like T3, T1.
That's right, yeah. It's for consistency of the meaning of products of multiple monodromy matrices. Because you see, so when you take T1, T2, T3, you can do, first of all, an exchange of this one, and then an exchange of this one, for example, and then an exchange of these ones. So then you get 3, 2, 1. But you can also do it the other way around. Yeah, you can start with this and then complete it. And the end result has to be equal. Okay? So R12, R23, R12, R13, R23 is equal to the other way. So it's a purely algebraic requirement. It's a bit like the Jacobi identities that you would write for an algebra. Okay? So it's really the same idea, but now applied to these matrices. Okay? So you really have no choice. If you want to have a consistent meaning for functions of these things, powers, maybe, eventually we'll have Hilbert space operators, products and things that will have to have a meaning. When you write a product of two matrices and things, it has to be unambiguous what you mean when you've got multiple things. And this ensures unambiguous meaning for any object in the free algebra of your monodromy matrices. Free algebra meaning, take arbitrary combinations of powers of these things. Okay, so it's really algebraic closure of all these objects. Okay? So now, because I've chosen the form of the R matrix, I get, through the Yang-Baxter equation, just with simple algebra, some constraints on B and C functions. Okay? And just for orientation, so you know what we're doing, we are now looking for commutation relations in Hilbert space. And these will come about because T1 and T2 are represented as matrices with elements being Hilbert space operators. And R T1, T2 is going to be T2, T1, R. R is scalar. So really, R T1, T2 is equal to T2, T1, R. It's a table of commutation relations in Hilbert space. Okay, that's what we're doing. So here we've got some constraints. And now what I'm going to want to do is I've got my constraints like this. And that's it. So, if I can find functions B and C that fulfill these equations here, then I've got a bona fide R matrix because it fulfills Yang-Baxter. And of course, the inversion relation of it and whatnot is trivially satisfied with these constraints here, then Yang-Baxter with these. Okay, so, and we haven't specified the little functions B and C. Still completely general at this stage, provided they obey this, then we've got stuff. So now we shortcut. We say, okay, stop the choices. let's just examine the consequences of what we have chosen up to now, leaving all these things arbitrary. What are the consequences? Well, we now have these little functions b and c, and we had these operators a, b, c, d in Hilbert space. So I write my RTT is TTR relationship explicitly. RTT is this. It's a good thing we're not doing this on the blackboard. TTR is this, okay? And now I can read off from this a set of commutation relations in Hilbert space between operators A, B, C, D. I haven't told you even what the Hilbert space is, but I've got all the commutation relations that I need. This is not a usual Lie algebra in which bilinears commuted map onto linears. This is a quadratic algebra. Namely, products of two commute into products of two. Okay? And that's it. So these are the commutation relations. We still don't know what these operators mean. We have some friendly commutation relations. We have some unfriendly commutation relations, but kind of friendly, you know, difficult people, but you can still get along with them because they do this, and you know, and you can control this. But we still don't know what the functions are. We don't know the meaning of these operators, but we now have a full set of commutations in Hilbert space, not knowing what Hilbert space is. It's kind of cool, no? So these are all the commutation relations that come from Young-Baxter. Okay, and then, yeah, so there are, in the notes here, you've got lots of notational conventions that help you map the literature because there are different choices made. So these are just the same commutation relations in a different notation. Okay, so now, once again, I don't want to yet go further in my choices. I just want to see what I've got up to this stage. Well, let's now talk about eigenstates of the transfer matrix, because the advertisement for this was that we could just plug these out of the air. So, what's our transfer matrix? The transfer matrix was the trace of the monodromy matrix in auxiliary space. Monodromy matrix is A, B, C, D. Trace, sum of diagonal elements, A plus D. Okay? Eigenstates of the transfer matrix, therefore, are diagonalizing this combination A plus D. So now I assume that there exists a state in the Hilbert space that I have not yet specified, the Hilbert space itself, but I assume the existence of a state, pseudo-vacuum or reference state, denoted as 0 here, that has the following properties. I assume that this state diagonalizes A and D simultaneously. This is possible because my commutation relations showed me that both were compatible. So I assume that A operator on reference state is scalar function little a on reference state. Same thing for D. And I assume that the C operator, because it's like off diagonal, you remember it's the lower diagonal thing, I assume that it's like a lowering operator. And therefore, it annihilates the reference state here is a highest weight state as far as C is concerned. Okay? So, or, lowest weight state, depending on your preferred nomenclature. In that case, then the reference state is an eigenstate of the transfer matrix with eigenvalue little a plus little d. Okay? Now, the fun bit is that if we assume that there exists a reference state, then we have a whole collection of eigenstates of the transfer matrix obtained by repeated action of the B operator, the upper diagonal element of our monodromy matrix. And what I do is that I take the reference state and then I act on that state with this B operator at parameters lambda j that are at the moment arbitrary. And now I use the commutation relations to compute the action of big A and of big D on these states, because I'm looking for eigenstates of the transfer matrix. So I use the algebra that I showed you before, and I compute the action of A on this product. So for this, I just need to commute the A operator with the B's until I hit the reference state, at which I pick up the scalar function little a. It's a bit complicated, but you can do it. And you can write this action as two different terms. One in which you end up with the same state as you started from, but with a scalar valued function in front. And one in which you've popped one of the B's into a different value of the rapidity. Okay, just algebraic exercise to do this. You can do the same for the action of the D operator. And now the magic thing is that we obtain an eigenstate of the transfer matrix if this term here obtained from the D cancels that term here coming from the A, the kind of off-diagonal term. So if this big thing here cancels this big thing here, then I have an eigenstate of the transfer matrix. And this condition is a purely algebraic condition involving the eigenvalues of the A and D operator on the reference state and the functions defining for me the commutation relations, namely the entries in the R matrix that I have not specified yet. At that stage, the only thing you know is the dimensionality of your auxiliary space. You know nothing else. However, you now have a whole set of eigenstates. Okay? The transfer matrix is diagonal on these states. The eigenvalue of the transfer matrix is again a combination of all these scalar functions that you've known. Am I going too fast, or are you kind of digesting it? Question? Little c. Or big C. You could do it the other way around. You could use a kind of pseudo-vacuum where you interpret things the other way around. So it would be then a lowest state instead of a highest state. Yes, you can do that. And it is algebraically equivalent if you have a finite dimensional Hilbert space. Yeah. Maybe later it will become clear. But this is just it. Okay, so now these are just extra equations for later convenience. You've got some things, but then you don't have that. Okay, so then just another little thing that you can do. You can also define a dual state to the reference state, namely the bras 0. You define it to have unit norm in this way. It has the same eigenvalues, or I mean, you can choose to have it like that. And now the action of the B operator, which was like the raising operator on the reference state, is now the one that annihilates the dual state. Okay, so that just allows you to use the usual bracket notations for states. Now these dual states, instead of being created by the B operator, they're created by the C operators. Okay, and you can, for example, look at scalar products and things like that. The point is that now you have a basis of eigenstates of your transfer matrix with orthogonality between states that are created by different sets of rapidities. So one choice of rapidities here gives you one state, and if you make another choice, then these states are orthogonal. That's the usual argument, where you evaluate the eigenvalue of the transfer matrix left or right, and that has to be compatible. Therefore, it's only non-zero if the states are the same. Okay? So what we're saying here is that it's kind of cool because we haven't even specified the Hilbert space. Not only do we not have a Hamiltonian, we don't even have a Hilbert space. However, we know all the commutation relations, and we know all the states. Okay? So now, what are we going to try to do? We've done everything we can up to now. So in order to go further, we need to specify the R matrix. So we will make the simplest non-trivial choice for the R matrix. And here, just a little bit of physical reasoning. That's the way I like to think about it. When we think of particles scattering with each other, what do we kind of think of? We think of like a fixed momentum wave hitting another fixed momentum wave. If the wave vectors coincide, then there is a big resonance between the particles, and they kind of interact strongly. They know about each other very, very much. If they have very, very different momenta, then they kind of go through each other without scattering. There's no resonance. It's like the way it is. So in my R matrix, I know that these elements define commutation relations. And I would like to have something that is very, very important. You know, I see a lot of effects of the ordering if the momenta coincide. But if they're very different, then I want that to be lower. And if the momenta are infinitely different, I just want this to be 0. So because I like complex analysis, Cauchy's theorem, and that sort of thing, I'll just declare I will make a choice where the basic entry in the off-diagonal bit of the R matrix is just a single pole. Okay? And when the rapidities are going to coincide, then somehow this is going to give me something significant. Then so I make this choice here. The C function is a single pole that I'll put somewhere. Don't specify what it is, don't specify that constant here. And now I'm looking at the constraints from Yang-Baxter. This tells me that I can make one consistent choice. B and the C functions share poles. I have to fix the B to this. Okay, so that's the choice I'm making. That's the consequence of this choice. So now my R matrix is given by this explicit R matrix here. And this is known as the rational R matrix. Okay, so let's see what the consequences of that choice are. Well, so I combine just unit matrix and permutation matrix, and that's just the value of this R matrix here. That's it. Okay, so what does this tell us? Well, it tells us in detail what all the commutation relations are. Okay, now everything is specified for the commutation relations. So now what I'm going to need to try to do is to define the monodromy matrix itself. I will try to construct something where, because I want to specify the monodromy matrix, I need to specify the Hilbert space now. So what am I going to do? I'm going to consider a Hilbert space. I don't want just a simple 2x2 space. I want something more complicated. So I will do a product of 2x2 spaces. And I'll declare that my Hilbert space looks like, indeed, two-dimensional spaces tensored next to each other. And now I'm looking for a monodromy matrix that satisfies R12 T1 T2 is equal to T2 T1 R12. But I already know that the R matrix satisfies Yang-Baxter, namely R12, R13, R23 is equal to. So wouldn't it be handy if I could just say, look, let T monodromy matrix be like R? Then it's automatically fulfilled. So I will say that the monodromy matrix is a product over all these different, call them sites, of a matrix that is simply the R matrix, evaluated at some point. And then automatically, because of Yang-Baxter, that means that my monodromy matrix satisfies R12 T1 T2 is equal to T2 T1 R12. That's it. I'm done. But because I know what the R matrix is, I can now calculate what the monodromy matrix is. It's the product of these matrices. Okay? So I literally calculate the monodromy matrix. And I get a matrix, and I look at that matrix, and you know, it's got some properties. If I evaluate it at certain points, I get simple operators. But I now know my monodromy matrix fully. Okay? And so, yeah, these are just little properties in there. And now, because I know my monodromy matrix, I know my transfer matrix, which is the trace and auxiliary space of my monodromy matrix. So I can write the transfer matrix itself as a matrix in this Hilbert space, which is now just C2 to the power big N, where N is the number of sites that I have. That's it. Okay? So this is the, and now that I know my transfer matrix, I can compute conserved charges. Okay? So if I take the simple transfer matrix itself, I realize in my first trace identity that what I've defined as the basic charge was just the log of this transfer matrix. And here, if I make a choice where all these parameters here are the same at each site, and if I choose to evaluate my transfer matrix at lambda equal to this parameter xi here, which is known as the inhomogeneity parameter, then if I evaluate my transfer matrix there, take the log, what do I get? I get an operator, which is just a permutation operator, which is really one site translation of everybody. So it's a translation operator that has eigenvalue of momentum, and I've just plucked it out of the air. Okay? And then I can go further, because I know that I can just take now derivatives with respect to rapidity of my generating function to obtain higher conserved charges. So I sit down and I do this for this particular choice of R matrix and monodromy matrix. What do I get? I need to do a bit of work. Need to be careful with the meaning of these things, blah, blah, blah. I do a derivation, and then I obtain an explicit expression for the first non-trivial charge above translation, which is a summation over adjacent site permutation and identity operators. Okay? And now I just use simple identities because I know I've got 2 by 2 spaces locally. I can write those in terms of Pauli matrices. Okay? Permutation operator is just the matrix with 1, and then in the 2 by 2 block 0, 1, 1, 0, and then 1 the diagonal. I've got a tensor product of Pauli matrices that corresponds when you sum to a permutation operator and identity. And therefore, I obtain an explicit expression for my first conserved charge, which is sigma j dot sigma j plus 1 summed over all j. Okay? And there you recognize it. It's just the Heisenberg chain. It's just the isotropic Heisenberg chain, which we have literally plucked from thin air. Okay? So this morally is an argumentation that the Heisenberg spin chain is the simplest exactly solvable model that you can possibly come up with that is non-trivial. At each step, you have made the most simple, non-trivial choice. And that's what you ended up with. Of course, now you can go back and say, hey, what if we tweak that choice and that choice and that choice? Well, then you get higher spin chains. You can get more complicated models. If you choose locally an infinite dimensional space, you can get Lieblinger and all these things. Okay? You see the liberty that you have. I've given you a whole menu of choices. You know, it's not like you've got entrée, main course there. No, no, no. You've got, yeah, lots of choices. You choose the dimensionality of your auxiliary space. You choose the R matrix that you have, the R matrix being a matrix. Therefore, if you change any single element in that R matrix, you've got a different R matrix. If you change the function of one of the elements, you've got a different R matrix. Okay? And then once you've got that, you need to make a choice for your monodromy. We took the simple choice of saying monodromy is just R matrix. You don't have to do that. There are other matrices that will obey RTT as TTR for the same R matrix, but just a different choice of the monodromy matrix. Okay? And you choose your local Hilbert space, what it means. You choose how you maybe tensorize that thing, what these all mean. And once you've made those choices, then you get a model. Okay? So that's the idea. The algebraic beta ansatz essentially is a thing where you solve formally all models once and for all. That's it. And the rest is representation theory. You choose a representation of the algebraic beta ansatz, landing you onto a specific model. Okay? So that's the kind of magic plucking from thin air of the Heisenberg chain. Okay? Now, what does that afford you further to this? Well, let's just make very few quick statements. First of all, these conditions that we had for states to be eigenstates of the transfer matrix, I can now write explicitly. And these equations take this form here, okay? And once you clean up your choices a little bit, let me just maybe do this straight here. So this is really like the summary of all the things. Once you clean up these choices, what it gives you is the full set of eigenstates of that system and the constraints that you have for the choice of these rapidities are the beta equations. So we have plucked the beta equations from thin air, okay? And that's it. So now that's the full algebraic picture for the isotropic Heisenberg chain, okay? Is that kind of okay? You at least get the story, right? So you'll have to work to fill in all the blanks, but all the notes are online here. You're welcome to do that in your time. But now you can tell your family, you can break the good news. Did you know that the Heisenberg spin chain was the simplest, non-trivial quantum model you could possibly write down? Yeah? Why? Well, our matrices, blah, blah, blah. And you try to rehearse, try to tell the story to your cat, rehearse it, and then your family, and then your friends, and you know, you'll live happily ever after. Okay, so that's the idea here. Now, let me just jump over. Yeah, you can do this. So, for example, here I give it to you for the XXZ as well, but again, you can just look at it. Different choices for the R matrix lead to different models. Now, let me make a couple of statements of things that are needed for further purposes. There is one result due to Nikita Slavnov, 1989, which is, I think, the single most important formula in algebraic beta ansatz. And what is this formula? It is the overlap formula between two states, one of which has to be an on-shell state, namely the rapidities in that state obey the beta equations. Therefore, it diagonalizes the transfer matrix. But the other one can be completely arbitrary. Nikita Slavnov was able, by just looking at commutation relations of this, to give an explicit expression for that object. Remember, the beta states, when we wrote them in real space, were factorially large sums of different terms. The overlap between two states, one of which only is an eigenstate. If they're both eigenstates, then this is just the orthonormality condition. So nothing new here. But if they're different states, then the overlap between these two states is given by the determinant of a matrix whose entries are scalar valued meromorphic functions of the rapidities involved. And it is completely explicit. Matrix entries are really like derivatives of the transfer matrix. So that means that if you're a smartass and you know the rapidities, you can plug that in that formula here, compute, and get a numerical value for what this is. Okay? So that's one extremely important element here. Single most important, possibly even the most beautiful result in algebraic beta ansatz, this thing. Then, what we want to achieve is contact with physics. Namely, we want to be able to talk about physical operators in the language of algebraic beta ansatz. What are our physical operators? If we look at the Heisenberg spin chains, these are the local spins. But the operators we have are A, B, C, D. So what's the relationship between spin operators and A, B, C, D? And the treatment of this is known as the solution of the quantum inverse problem. And again, you'll find all details in these notes here. Very simply, it requires you to write down the representation of the matrix in the notations you've chosen in terms of just tensor products of Pauli matrices. And then if you look at this hard enough, you will notice that there exists a mapping, which is complicated but explicit, between matrix Pauli matrices at given sites and products of ABCD operators. Now, you'll be pleased to know that despite your love for the simple spin-half representation of SU2 algebra, these things are monstrously complicated to deal with. But these things here, they are very friendly, okay? Because you have A plus D. A plus D is transfer matrix. Transfer matrix to a certain power. I know the eigenvalue, I can take the power. This is just the translation operator. This is just the translation operator as well. And sigma Z is just A minus D. Sigma minus, like adding an excitation, is just the B operator. Sigma plus is just the C operator. So now, when we create a particle, we pull one spin down. That's what this means. And now I've got this representation for the operators in terms of ABCD. And I can now throw that representation in the Slavnov formula. And when I do that, I obtain an explicit expression for the matrix element of a spin operator between eigenstates of my theory. Okay? And this matrix representation, this matrix determinant representation, I mean, for example, you've got this one here. So how does it look like? I've got, for example, for the spin down operator, I get this, this expression here. The matrix element of the spin down operator between two states is just the determinant of a matrix that I know explicitly, if I know the rapidities of the states involved. Okay? So without you realizing it, now we are in a position to answer any question you might have about expectation values of products of spin operators at different space-time points in a spin chain. Okay? So this is what the algebraic Bethe-Ansatz gives to you. Okay? So this is like the summary of the story. I took a little bit longer than I expected to do this, but you know, still, you know, like shortcuts. Yes.
So it's just the same.
Absolutely. So the SU2 algebra spin-half representation from each of the local spin-half spaces is fully reproduced by the complicated ABCD commutation relations.
And for higher spin also?
For higher spin also, it will automatically be fulfilled. So if you have there are spin 1 integrable chains, spin 3 halves, etc., etc. There's a whole hierarchy of spin chains. And you can construct the algebraic Bethe-Ansatz for all these things. And in each case, everything is faithfully reproduced. You get very simple algebra for the spin operators, very complicated algebra for ABCD, but it is fully compatible. It is really, there is nothing hidden, nothing not explicit, no cheating. Everything is really absolutely, completely nailed to its place. So it's really, you can show, you know, so maybe the only assumptions that you are making that are very, very difficult to prove actually are assumptions about completeness of the set of states that you have. So here we're kind of doing the same assumption that, that we, you know, I won't say we did because we didn't really, but you know, that you might have seen fly through the room as I was saying it. When we solve the Bethe equations, if we find all solutions to these algebraic equations, then we have a complete set of states. I did not prove this to you, okay?
But also, like the construction of transfer matrices that BC, we like assume them being Leibniz operators, and A and B, we assume that they will act on our states. It will be agent state. So
that's right.
It's like also an assumption.
It's an assumption, but you see, when you think of any representation of an algebra, so where you really explicitly have to give me, for example, a matrix version of what you mean by sigma plus, then what are you going to do? You're going to need to put an off-diagonal element in that thing. Yeah, because otherwise, if it's just diagonal, you're not going to be able to invoke the usual ladder arguments with termination if you've got finite dimensional representations and that sort of thing. So it's very natural to associate off-diagonal elements of our monodromy matrix to elements that somehow create or annihilate objects that we will interpret as particles. I don't really care if for you the upper off-diagonal element is creation or annihilation, as long as it's not preservation. Yeah? So you tell me what you prefer, and we'll rewrite everything in there. It's a totally physically immaterial choice. No meaning. It has the same algebraic consequences if you keep consistent. The only thing you have to do is make a choice and stick with that choice, right? Because if you change choices, then okay? Other questions, yeah? Okay, so great exercise. So if you go to the third charge, you can just take the second derivative of the log of the transfer matrix. And what you will get is a conserved charge involving 3 consecutive spin operators on sites j, j plus 1, j plus 2. And you can do that. It's explicitly, it's not so complicated to do. You can do it with a fourth and things. You can actually write a more or less generic expression for all these things in terms of products of spin operators. And in general, charge q at nth level involves a product of, I mean in my labeling here, n minus 1 adjacent spin operators. So this trace identity logic, it never really terminates. I can take a number of derivatives with system size, you know. I can take exponential of system size derivatives of the transfer matrix, and I will still get operators. But at some point, the operators will close in on themselves. And they start closing in on themselves when you've generated a number of conserved charges that coincides with the dimensionality of your full Hilbert space. So with this, you can construct a basis, if you want, for your conserved charges. It contains everything. Now, the version that you get of the charges, realistically, is useful for the first few charges. You know, up to an index, which is little o of system size. If it becomes much higher than that, then it's better to use a different basis for these more complicated non-local charges. And I will briefly mention stuff about that when I talk about quenches.
I guess this is why we are speaking about integrability when we have extensive number of charges for the system.
We can have a whole evening discussion about the meaning of quantum integrability. And if you thought I had strong opinions yesterday about publishing quantum computing and stuff, just wait till you hear my opinions about definition of integrability. Yeah? For tonight. If we had wine again and stuff, you would have a fabulous evening. Yeah? Yes.
Yesterday we mentioned some conditions for the Gansets to hold true, like the factorization of scattering and so on.
Yes.
Is there a way to see this in this algebraic Gansets, or?
Yes. So very good question. Essentially, the Yang-Baxter relation for the R matrices can be drawn into different ways. So very often people draw it like this. So you've got 3 lines coming, and let's see what the best way would be. Let's say I do 3 lines like this. So the way I interpret this is that there are different scattering events occurring, and maybe I do like 1, 2, 3. Okay, and then what that means is that if my time flows like this, it means I'm scattering 1 with 2, then 1 with 3, then 2 with 3. But the Yang-Baxter relationship tells me that this is going to be the same if I do it the other way around. So just imagine that I'm taking this line here and I'm pushing it through here. So then I get a drawing like this, where again it's 1, 2, and 3. But now I'm scattering 2 with 3, 1 with 3, and 2 with 1. So this equality here is the Yang-Baxter relation, but the way you can physically interpret it is as factorized scattering. Namely, I'm scattering 3 particles, and you don't need to tell me the order in which it occurs because the scattering is factorized into products of 2 particle scatterings, and therefore it's consistent. So in a non-integrable theory, there would be a difference between these processes occurring in different successions in time. But in our case, there's no difference. So that's the way you interpret it. Yeah, but then of course the language that we have here is for the R matrix, and you'd have to make the mapping back to scattering of wave packets. I'm seeing no particle production there. But really mathematically, it boils down to this. You can derive factorized scattering from this. It's an immediate consequence of these choices. Okay? Any other question? Good. So let me not screw up my time. I've got until 12:15, right? Is that correct? Okay. You weren't here yesterday, Thierry. It was like completely ridiculous because I rushed and I finished after an hour. And then we all went for coffee. And then at some point, you know, Patrizia went and said, it's 10:15. You're still meant to be lecturing. I was there sipping my coffee, you know. What? So then we ended up outside for a little extra 20 minutes. But yeah, so today I can hammer you continuously for another half hour. Very good. So now we go back to the content of today, which is really the use of all the things that I have shown you in the context of integrable models in equilibrium. Okay? So let's see how we do with all of this. So once again, just very, very brief rehash of everything that we've said. So the general idea of everything we're going to do here is we're going to ask interesting questions, but frame them in the context of integrable models. Namely, the states that I will work with will be explicitly specified beta states. I will apply some operator on those. Perhaps I'll flip a spin, perhaps I'll time evolve it with some strange things. Nonetheless, it doesn't matter because any operator that you will have here, I can use my catalog of mappings for spin chains, for example, spin operators to algebraic beta ansatz operators. I can write this in terms of ABCDs, complicated products of these things. And I know all the algebraic properties of these things. Therefore, in principle, if I'm working in the basis of beta states, I can perform any calculation you want. Matrix elements of operators in the beta basis are given to us by 2 things. First of all, the solution of the quantum inverse problems, which allows me to write any operator as ABCD, you know, schmoozy functions. Then, once I've done that, I invoke Slavnov's theorem, where I will act with ABCD on one of the states here. In this case here, both are eigenstates. So I would act, after transforming this to ABCD using solution of quantum inverse problem, I would have ABCD stuff that I would then act with on the state and destroy its eigenstate property, because now I've got junk in there. However, all this junk creates for me states that are still written as products of B operators on reference state. It's just that the rapidities in there are not anymore solutions to beta equations. But that's where my friend Nikita saves the day, because he says, I don't care. I just need one of the states to be an eigenstate, and then you're cool. But this is still an eigenstate. Therefore, I can invoke Slavnov's theorem and give you an explicit function of the rapidities in the left and right states, describing the matrix element of that operator. That's the idea. Okay? What we can calculate realistically are matrix elements of relatively simple operators. So in the case of a quantum spin chain, we will be looking at few point correlation functions of spin. Most importantly, 2-point correlation functions of spin, but now evaluated at different space-time points. And of course, so like Thierry already kind of showed you a little bit, these are important correlations because they're the things that you need to compute if you want to use a Kubo formula, linear response theory, onto any experiment that your friends are doing. So for spin chains, I'll show you a lot of stuff obtained with inelastic neutron scattering. And then for the Lieb-Liniger gas, you're looking at equivalent things where, for example, you're doing dynamical density-density correlations. Thierry already showed you the plots that I did for this in 2006. I mean, all these, centuries ago. You can also look at simple things like this, and then the I know, but it doesn't feel like that, does it? Yeah. So the experiments here are for Bragg spectroscopy, some interference. Again, Thierry showed you some things on this. I'll just show a couple of extras on this. The technology needed, we've just seen here in the first hour. So algebraic beta ansatz, you think about it like the second quantization for beta ansatz. ABCD goes to operators. You just use Slavnov, and then you're done. Okay? So this is really the one-slide summary of everything I've told you earlier. Question, yes? No stupid question.
How are these
You're asking me?
You can't solve anything, but I think at some point they are really like super hard.
So what I would say is that the whole next half hour is going to be answering this question by specifying what can be done and how. And then you'll see both how hard it is to do that and how hard it is to go further. So I'll keep your question in mind, and I'll look at you as I do slides. And each time I look at you, it's because I'm giving you one element of the answer to this. Okay? So, yeah. What do? We do basic quantum mechanics. So we write the correlation functions in a layman representation. I presume most of you have seen such things. You write a correlation function by taking a Fourier transformation. You've got the time evolution given to you by just the unitary time evolution, e to the minus I omega. Because why? We're working with eigenstates, therefore I can diagonalize the Hamiltonian, therefore I can diagonalize the unitary time evolution operator. Therefore, all the time dependence that I have, if I take a time Fourier transform, is expressed in terms of the energies of the states that take part. We can afford to do this because we are working with exact eigenstates. If you're doing any perturbative thing, this is not going to work. But here, because we've got exact eigenstates of the Hamiltonian, we can immediately have exact coherence between all these contributions. So first building block is the eigenstates. So I've shown you how to compute energies. I've shown you how to construct eigenstates. So we got that, beta ansatz. There's another technology which is dual to all of this called the vertex operator approach. I will leave that to the outside just to say that in one word, it applies to zero field spin half antiferromagnets in the infinite size limit, strictly in the thermodynamic limit. It relies on the existence of a quantum group symmetry to the problem, and then the representation theory of that thing gives you physical things, but it's not exactly beta ansatz. It's more complicated. If you want to know more about this, I'm very happy to give you details about this. Second thing we need are matrix elements of physical operators, but that's cool because algebraic beta ansatz gives us that, as I've told you. And also within vertex operator, you can do this. And now comes the tough bit, which is summing over these intermediate states. Now, what is this simple summation here? It is a summation of a number of terms equal to the dimensionality of the Hilbert space that you're dealing with the restriction. For example, if you work at finite magnetization, you tell me which operator this is. It's going to land onto a specific magnetization sector. And then I can fix magnetization. This is always an exponential in system size sum. Okay? So here, sometimes you can do analytics. I can count them on the fingers of one hand. Okay? spin chains in zero field if I restrict to 2 and 4 spin-ons. That's it. Okay? All else has to be done numerically. So although I'm a theorist, I was given a computer when I was very young and, before you were born. So I have no hesitation in using computers in order to compute things with a numerical value if I am not able to do the analytics. Okay? So most of the results that I'll show you are actually numerical results. And numerical here, I insist, is purely evaluational. It is not simulational. Okay? I'll show you how to do this. So what is the idea behind Abacus, this code that I wrote for this? Well, the idea is that we've got a whole lot of contributions from all possible intermediate states. And I will want to capture the important contributions here. And not all intermediate states are of equal importance to, for example, some rules that you would evaluate to assert the quality of your correlations. So the idea of Abacus is that you think a little bit and you find the most important contribution. And you start from there. And then you deform the state a little bit in order to find neighboring high contributions. And you sum up going down as slowly as possible. So you try to win from the top. So you climb the mountain from the top down. Okay? So what's the result? So these are just like colored versions of the plots that Thierry showed. Lieb-Liniger, density, dynamical function, momentum on the horizontal axis, frequency on the vertical axis, color coding is intensity of the correlation. Low interaction value, most of the correlation is carried by free particle-like modes with dispersion relation almost equal to p squared over 2m. If you put the interaction very, very strongly, you get more complicated things. So, low interaction, high interaction here. Interaction parameter C is just a tunable thing in this. Okay, so that's one example result. So in order to get these figures here, what I do, these are ground state correlations. I construct the ground state by solving the beta equations numerically. It gives me the rapidities for the ground state. And then I start creating excitations around the ground state by moving quantum numbers in my beta ansatz and resolving the beta equations. Then I put those rapidities in the determinant formula for the matrix element of the density operator that I know from solution of quantum inverse problem and Slavnov's formula. So I compute a determinant of functions of these rapidities, and I get a result. And I put a little point in the plot at that energy and at the momentum corresponding to the momentum difference between these plots with a height equal to matrix element squared. So this is a great big collection of gazillions of little points. Okay? Each place where you look, there's a family of states that contribute to the correlation. Okay? And you can assert the quality of this correlation here by looking at sum rules. So these calculations, again, they're from a long time ago. So these were for a couple of hundred particles. And the saturation of the sum rule that you can assert is of the level of 99%. So essentially, as far as experimentalists are concerned, there's nothing else. Okay? Correspondence with excitations. We didn't talk very much about the excitations around the Lieb-Liniger state, but there are two things. So your ground state is like this Fermi C. These are quantum numbers. And the particle-like excitations, so-called type 1 modes of Lieb-Liniger, follow the upper branch here, and the hole-like excitations follow the lower branch here. Okay, and so Luttinger theory would describe well what occurs in these regions near the low-frequency domain. Okay, so that's, these are things that you have. So this is a movie of an impossible experiment where you measure the Bragg spectroscopy, Bragg scattering amplitude throughout K and omega as you tune up the interaction parameter from weak to strong coupling. Okay, it's fun, you can do this. One thing I do want to say about these plots is that because we are using exact eigenstates, we absolutely do not care about the value of the energy where we are sitting here. The accuracy is the same because an exact eigenstate is as exact at low energies or at high energies within beta ansatz. It doesn't matter. So that's the great thing, the great luxury that this method affords. You are compelled to work with an integrable model, but if you swallow that pill, and you live, then you're happy. Okay? So that's the idea. And now this is the equivalent in the spin chain. So for the spin chain, we're here dealing with spin-spin dynamical correlation functions. And this has different characteristics to the Liebling gas. First of all, the simple excitations that you have for this, so-called spin-ons, are essentially like holes in the Fermi sea. And this lower branch here corresponds to one spin-on going from one side of the Fermi sea to the other side of the Fermi sea. This is essentially a two spin-on continuum where the spin-ons trade with each other energy and momentum, and they carry the bulk of the correlation here. So this is a calculation for a spin chain of 500 sites, and once again, the saturation of the sum rules is of the order of 99%. So now, turn back to you. Partial answer to your question is that despite the fact that there are exponentially many states that can work as intermediate states, all but a measure zero subset of them contribute, all but a measure zero set do not contribute to the correlation. Namely, a measure zero subset of the intermediate states contributes fully to the correlation. So if you give me an epsilon, which is your target measure for the deviation from the exact result, maybe you tell me, I want the correlation function to 99.99%. How many states do I need to put that for a 500-site chain? Then the answer to this question is something of the order of n to the power 6, as compared to 2 to the power n, modulo magnetization. Measure zero subset. So the excitations of beta states are extremely well connected to local spin operators. Namely, the action of a local spin operator creates only few excited beta states, not exponentially many. Because the beta ansatz has already sorted for you completely all interaction effects to all orders, and the mapping from sigmas to ABCD has done that for you at the operator level. And the two work well together. So although it is difficult to do this, I need to compute the rapidities for the ground state. Then I need to compute the rapidities for each and every eigenstate that I'm going to want to put in the trace. And then for each of these eigenstates, I'm going to need to compute the Slavnov determinant. Okay? Each of these steps is of order n cubed, because these are determinants. And I put something like, you know, in this case here, again, I'm going to put stuff up to, say, 8 spin-ons. And the rest is really utterly negligible. So yes, it's complicated, but it is still exponentially easier than doing anything that would correspond to exact diagonalization or something. Yeah, so that's why the answer to your question is really both at the same time. It's complicated, but super easy. Does that help? Maybe that doesn't really encourage you or something. Yeah? So, like, big codes. By the way, you can find my code online and laugh at my 20-year-old C++ skills and things, but that's the way it is. Yeah? So I'm a child of the 90s. These are general correlations for an isotropic chain as you change the field. Again, you can just play these fun movies. Just jump over this, because once again, time is dangerously going ahead. Okay, so maybe some more physics fun associated to that. Ludwig Fadeev is the one who really understood with Leon Takhtajan what the fundamental excitations in spin chains are, these spin-ons. And here again, we can play games with integrability that are difficult to do otherwise. What I'm doing here is I'm starting from the ground state of the XXX chain, and at t is equal to 0, I'm flipping the spin on site 0 to the upwards position. And then I'm time evolving, and I'm measuring SZ as a function of time for each site. That's the way it looks. So I get these waves of staggered magnetization moving from each other. These become ballistic-like excitations that correspond to the spin-on wave packets that you would have for this. So when you do neutron experiments, you're essentially doing that in a certain place and then measuring the effect on the magnetization. So how does correspondence with experiments work? For spin chains, it works rather well. It's a very easy experiment to do. Namely, what you need to do is the following thing. You need, first of all, maybe the first motivation. So exchange things are very important in condensed matter. One of the thoughts is that high TC can be driven by magnetic exchange interactions. Nobody knows how, but people are still looking at that. 2D high TC materials, they've got 1D equivalents of this, like this strontium copper oxide that buddies in the US did neutrons for, and I gave them some theory for that. So how does inelastic neutron scattering work? Like I said, it's very easy. Neutrons carry no charge, but carry a magnetic moment. Therefore, they really penetrate quite deeply in matter and then interact with local magnetic moments in your chunk of matter and can induce spin flips. When you induce such a spin flip, you create a kind of discomfort in your antiferromagnet. Your antiferromagnet does not like parallel spins and therefore tries to expel them. So these things start moving, and these are the waves that I showed you before. These are the things that become spin-ons, and you see they're created in pairs. So going back to the experiment, like I said, super easy. You take a nuclear reactor, and you drill a hole in its concrete housing so that you have thermal neutrons coming out. Thermal because they've got a distribution of velocities. And now there's this absolutely high-tech device. I still can't stop my wonder of how complicated this thing is. It's called a chopper. You need to have single velocity neutrons in order to really know the energy of these things. So what you do is you have two little doors, and if you want fast neutrons, you go open, open, close. If you want slow neutrons, you do open, wait a bit, open, okay? Super high tech, huh? But it works. So you get bursts of neutrons hitting your target. And when the neutrons hit your target, they are deflected by the magnetic interactions. Namely, they change direction and they get retarded in their velocity, if you want, by the deposition of energy in the sample. So you've got a bunch of detectors. It looks like a kind of inverted fly's eye, kind of half cupola of detectors, which are like devices, about that big, that do a click and record the time when a neutron hits. So you get data for the intensity of the neutrons that hit at any of these detectors. And because you know the time at which the burst occurred, you knew the speed of the neutrons. And if you measure the time at which they're recorded, you know the speed after scattering. Therefore, you know the energy deposited. Okay? So it's as simple as this. And now, so that gives you measurements via neutrons of these space-time dependent correlation functions in the spin chains. And then, you can look at this. This is one example where you correspond the beta ansatz calculation with the experiment. Here, the beta ansatz is like convolved with experimental resolution. That's why it looks a little bit unsharp. So the correspondence, it really works also at higher energies. Yeah, it's the luxury of that particular method. Okay, so now I've got lots of examples of these things. This one I thought was really fun because it's a crystal that some of you might have synthesized in high school, or maybe you did that at home. I don't think you did the deuterated version of it, however, but nonetheless, that's it. It's a crystal which is very easy to grow. In fact, it is so easy to grow that this artist in the United Kingdom, Roger Hjorns, coated a whole apartment in London with copper sulfate. And he really had multi-rooms things. It's all this beautiful blue that you have there. And then I contacted him and I said, do you realize that you have the largest collection of Heisenberg spin chains in the known universe? And yeah, there was no interest to go any further. He didn't care, but anyway, so that was it. Try to excite people in the public about integrability and whatnot, and you just like spectacularly fail, and you say, fine. Okay, so this was an interesting experiment here because there is no fitting parameter between the experiment and the theory. The experiment is able to measure the value of the exchange constant, and given the exchange constant, That's the only number I need in order to give the prediction, the quantitative prediction for the scattering amplitude. So it's a 0 parameter fit over this full k and omega range of values here. Okay, so this worked quite well. And it's really nice because this particular experiment was the first one to achieve an accuracy which was sufficient to discern between the predictions of integrability and the predictions of field theory and other approximations that you can smartly put on this. And the deviation is at higher energies, where once again beta ansatz is comfortable, but these other methods start being less comfortable. So it was possible to like do a really, really good match with these things. Yeah, lots of other crystals. So KCUF3 is another one for which there was a lot of data. You've already seen this. The same kind of logic here. High energy predictions are really accurate with beta ansatz. And the interesting thing is that there are now new sources for neutrons using spallation that achieve much higher intensity, and there's a promised reduction in the experimental resolution ellipsoid by a factor of 10 in both directions. So I'm kind of still waiting for this data to show up, and I'll be able to give them like ultra detailed beta ansatz calculations to try to fit all of this. Okay, so that's the context of spin chains. In the case of cold atoms, you've already heard from Thierry a bit how that works. So let me kind of jump through that very easily. You get these confined gases in 1D. Because of the interactions, there's a kind of propensity to the atoms to try to form, you know, melting-like but still crystal-like lattices where the spacing between the atoms tries to be very regular. And when you scatter light of this, of course, there's like a Bragg effect there, a resonance that picks up any like proto-ordering in the interparticle distances in there. Okay, so as you have, there's this experiment that was also mentioned by Thierry, Newton's cradle. I'll have more to say about quenches in my last session, but here essentially you get like full dynamics of this after pulsing your gas, and you can try to see what you get out of this. So we'll go back to these questions in the last session. There's another context where you can do experiments in cold atoms, namely atom chips. Here you're more confined to very weakly interacting gases, but nonetheless you measure some distributions that are fitted by beta ansatz calculations. This was done actually, it's a funny story. So this was done by an experimentalist like 3 doors down from my corridor, and he didn't know about me, I didn't know about him, and he ended up publishing with a theorist in Australia. So it was like literally the antipode, and then afterwards we realized how stupid we had been for not talking before. But so he's not doing that anymore, but that was like a seriously missed opportunity. Yes?
Question on the previous slide.
Sorry, yes.
Is it because it's in the Netherlands that it's an ideal gas?
Did I? Before that?
It's a joke, it's a joke, it's a joke. Don't worry, continue.
Oh.
With the caption of the you have ideal gas.
Ideal. Yes, I had never noticed. I will tell Klaas Jan. I'll say, oh, Klaas Jan, you screwed up. Okay, I had never noticed this. I guess I was just transfixed by the curve, but yeah. Yeah, so, okay, no, very good. Yeah, ideal indeed. Huh? Okay, so that's the thing. Then there are some calculations that I did with a former PhD student of mine, extending ground state calculations to finite temperature calculations, much tougher. So there, we need to increase the complexity substantially, because computing correlations on a finite entropy state means much bigger resummations than around ground states. Again, I'm happy to hammer you with these complexities if you're interested. So this was, again, fitting with experiments performed in Italy. So Chiara Fort was leading here. It's a group of Massimo Inguscio. Nicola Fabri was also the student doing all of this. The idea here is you do Bragg spectroscopy and you get these scattering amplitudes. The problem with these cold atom experiments is that there's no independent thermometer for assessing the temperature of these things. And the idea behind this was that through the scattering amplitudes here, and using the beta ansatz predictions, we could try to measure temperature via the shape of the correlations computed from beta ansatz at different temperatures. So that was one of the things. Now this was done in a gas of rubidium, so restricted to relatively low interactions. Later, the group of Hans Christoph Nagel in Innsbruck performed the same experiment in cesium gases, which have Feshbach resonance, which means literally that in the Lieb-Liniger model, the parameter C can be tuned through a range having a factor of about 500. So you can go from relatively weakly interacting bosons to very strongly interacting fermions. And then once again, you do the mapping and you try to assert temperature from the beta ansatz predictions here. So this is like the mapping to experiments that, that I can mention for all of this. Now maybe in honor of Thierry, I will just end in, we started 3 minutes late, didn't we? Yeah, I got 4 minutes. Okay, yeah, fine, 4 minutes on, perfect, yeah. Okay, so Luttinger liquids. So you already know everything about Luttinger liquids thanks to Thierry this morning. And now, so let me jump through that. Thierry already showed you how to write these models in terms of free bosons. You just need to know the velocity, and you need to know K, or U, and you know, U and K in your favorite notations. So yeah, this is really all the story there is. Okay, so let's look in detail at what the predictions are from Luttinger theory. Luttinger theory tells you, for example, that you've got density-density correlations that are successive power laws with different exponents. Luttinger theory sometimes fixes the prefactor of these terms, like this one here. However, the higher terms here, because they depend on the microscopics, they are not universal. The power law is universal, but the amplitude is not. And Thierry already taught you that this morning. Thierry already taught you also that the parameters that appear in your Luttinger theory can be computed from basic calculations in beta ansatz, where you compute energies, some susceptibilities, and then you fit. So this is like the traditional stuff. Now what one can do above that is, for specific integrable models, one can compute these amplitudes, glorifying the kind of correspondence. So that's the step that, that we did quite a few years ago. So the idea is that you're now looking at these correlations and you are computing the height, if you want, of the correlations at these further points. Okay, so the way you do this is that you really absolutely carefully do fits with the correlators, and these constants here, they really come from matrix elements themselves. So if you know how to compute the matrix elements in detail, and you know how to compute the summations over the states that contribute at those frequencies, then you obtain what it is. Okay, so in case of spin chains, then you're looking once again at values of correlations, really amplitudes of correlations at these points in the low energy subsector. Okay, so this is possibly the funniest publishing experience I have ever had. This is with the dear Adilet Imambekov that Thierry already mentioned. So it's a very tragic story. I maintain that this is the smartest young person that I've met in physics, like really off-scale smart. Totally, he was absolutely unbelievable. But so we started working together in the late 2000s. Unfortunately, he passed away in a mountain climbing accident in Kazakhstan. Sorry, that went a bit fast. So these are the papers that we did together. Actually, when he died on the mountain, he had one book with him, which was the book about the algebraic beta ansatz by Koryepin, because he was trying to understand what I was telling him about these things. So that's what we did. We computed these prefactors, these amplitudes from integrability, kind of feeding more material into Luttinger theory than had been done before. The usefulness of this is kind of fun because it allows you to also ensure that the whole thing is consistent, that the predictions are extractable from integrability. It has some utility. The fun bit, however, is when you try to break through the limitation of Luttinger theory that Thierry already taught you about, namely restriction to high energy, to low energies. Now, that's the question. Can you use Luttinger theory to describe excitations, correlations at higher energies? And there is a trick that you can use. So the idea is that, although traditional Luttinger theory is restricted to the vicinity of the Fermi points, if you are looking at relatively simple eigenstates at high energy, which are obtained by having single particles carry measurable energies, then you can still do it, because this is like having an impurity in a Luttinger liquid. And this impurity, due to its momentum and energy, is like a distinguishable particle that you can take into account using clever tricks. So Adilet really worked on that just before he died with Leonid Glassman and many other people. I mean, Thierry also contributed to all these things, but I mean, these are the initiators of that whole thing. So the idea of this nonlinear Luttinger theory is that you can look at correlations at high energy, but in the vicinity of these singular points that you have. Okay, so again, the advertisement here is that you're just able to glorify this catalog of correspondence between these things, and that's, you know, our good friend Adilet. And he was working in Texas back then, and I think he was really destined for, you know, great things. So an immense tragedy. Yeah. So if you go climbing, be careful, and also don't do it on your own. Okay. So yeah. Essentially, the rest here is just some extensions of this. I've got other things to say about correlations. I've got interesting mathematical statements also about this. There are these mathematical curiosities known as continuous but nowhere differentiable functions. I assert that for the case of the Heisenberg spin chain, the correlations are such functions. They have essentially, at any position, a certain order of differentials that diverge. Okay, but that's for the mathematicians among you. If you're interested, we can talk about this. And I'll stop here because this is for the next session. Okay, so, sorry, I went 2 minutes too long. Yeah, sorry.